Hey everybody, today we're going to talk simple DC circuits, but before we get into the basics of that, much like for the rest of the electricity unit, I'm going to compare it to gravity. So let's start by looking at some pretty pictures of waterfalls together. First and foremost, with this waterfall, you can imagine, let's go ahead and pretend that there's a pump down at the base, and that pump brings the water back up, circles it back around, and so the water is just going through continuous loop, down the waterfall, around the little stream area, up a pump, back across the upper river bit, and then down the waterfall again. And let's just pretend it's a continuous loop over and over and over again. Now, when it goes over this waterfall, it drops a certain height, which means it has a certain change in potential energy. And the amount of potential energy that the pump adds needs to be the same as the amount of potential energy that the waterfall drops. Otherwise, it'll come out a bit too high, or else it'll come in a bit too low and not get into the pump. So that change in energy always has to be the same. Now, waterfalls aren't always this simple. It's not always just a single waterfall and you're done. Sometimes you come across waterfalls that fall in different series of steps. Now, with each of these steps, it's losing a little bit of potential energy. Now, that change in potential energy between the steps might not always be the same. So delta U1 might not be delta U2, but the total change in energy overall has to be the same amount of energy that the pump on the other side uses to bring it back up. And sometimes it's not a series of individual little waterfalls. Sometimes water will branch off. Some will go to the right, some will go to the left, and they'll fall off different types of waterfalls next to each other. You could say they're parallel to each other. And no matter which path it takes, no matter which track it follows, that change in energy is going to be the same. So the current doesn't have to be the same in each of these waterfalls. Some might get more water than others, but the total drop in energy has to be the same, and that total drop in energy has to be the same as the energy supplied by the pump that brings it back up. And of course, every now and then you get some sort of combination of these weird setups where on one path, all that energy is dropped at once, and in another path, it takes a series of steps, little individual steps, but overall, the total change in energy is the same regardless of which waterfall you go over, and it's the same as the pump that brings it back up. Now, changing this to electricity terms, you need a few things to create an electrical circuit. So forget the water circuit that we've created, now we're into electricity. You're going to need a power supply. Some sort of source of potential difference, and remember, potential difference is just the same thing as voltage. So a voltage supply. This is basically going to be the equivalent of the pump that brings that water up. You're going to have a closed loop, so if the circuit's open at any point, it's not really going to work. You'd have to have a closed loop for the water as well. If water is getting out one side or the other, then you're eventually going to run dry. And you need some source of resistance, and I'll talk about that right now. Resistance is provided by a resistor, and it's measured in units of ohms, and this is just another base SI unit. Ohms represented by the Greek letter capital Omega. And the purpose of resistance is ultimately to slow the current through a circuit. If you do not have resistance, you'll have what's called a short circuit, and that can be really bad, and that's how things catch on fire. Then you'll have a battery or a power supply. This is what provides the voltage. Again, this is kind of the equivalent of the water pump. It brings it up to a certain level of voltage. Voltage and potential energy, if you remember from the lecture earlier, are really, really, really similar. It's basically just potential energy is the potential energy per unit charge is the voltage. So you can kind of think of those as being equivalent. Now the voltage is gained by the battery, it's brought up by the pump, and it's dropped over the resistors, which are kind of like the waterfalls. Then you've got current. If you think about what water current actually is at the base level, it's molecules of water flowing by. And the more molecules of water that flow by, let's say I dip my foot in the water and let the water flow over it, the number of water molecules that flow over it in any given second, that's my water current. Same deal with electricity. The current, denoted by letter I, is the amount of charge per second. So now we're not counting water molecules, now we're counting electric charge in coulombs. So current is just charge divided by time. It has to be a moving charge for this to work, so the amount of charge that passes by a given point at any given time. Current will be measured in amperes, charge will be measured in coulombs, and time will be measured in seconds. So 1 ampere is just a coulomb per second, and that's the unit of current. Which brings me to Ohm's law. This is kind of the holy grail of circuit equations. V equals IR. That's the voltage will equal the current times resistance. So, again, if I set up a power supply with a certain level of voltage, and I have a really low resistance, I get a really high current, and that's dangerous. So that's why you need some sort of resistance in any circuit you're going to be building. Now, Ohm's law can be applied to the entire circuit, which means the voltage pumped out by the battery equals the total current out of the battery times the equivalent resistance of the circuit. I'll talk equivalent resistance in just a second. It can be applied to a single resistor as well, so the resistor being the waterfall. Each little drop, each little voltage drop equals the current going through that resistor times that resistor's resistance in ohms. And it can be applied to a simplified group of resistors. A few little background things about circuits that you need to know. Again, since you have to have a closed loop, there's this law called Kirchhoff's voltage law that says through the course of one path around the circuit, the total voltage gained equals the total voltage dropped. Again, with the waterfall, whatever distance, whatever height the water drops off, whatever loss in potential energy in joules there, you gain from the pump. And it's the same. Now, if you've got multiple path options, like those waterfalls that we're splitting off, each path results in the same voltage drop. There's also a Kirchhoff's current rule, which says at a junction, so that's if you're about to split off onto parallel branches of wire, the total current coming into a junction is the total current leaving a junction, which sort of makes sense if you think about it with the water analogy as well. If I've got a bunch of water all in a river, and then the river splits, some will go to the left, some will go to the right. If I add the total left and right water, I should get the total from before it got to the split. No water was added, and no water escaped, just from the act of splitting. So when we start building these circuits, sometimes you'll find series circuits. This is kind of like those series waterfalls, the little drops as you go down, versus the parallel waterfalls, which is where the water breaks off, and each little path has its own waterfall. Now in series, each current is the same for each resistor, which kind of makes sense. There's nowhere else for the electricity to go. Oh, by the way, the symbol for a resistor is this little squiggly line. Symbol for the battery is one long line, one short line. And sometimes you'll see it doubled up. Short line, long line, short line, long line. But in a series circuit, the voltage drop across each and every one will add up to the total voltage from the battery. Just like those series of waterfalls. Each little drop might be different, but the total ends up being the same. Versus, looks like I forgot to label it here, versus a parallel circuit. In a parallel circuit, the total voltage drop is the same across each resistor in parallel. Just like with those waterfalls, no matter which path it takes, the waterfall it falls over is the same drop in energy. And this is only for perfect parallel. If you've got a little combo series in parallel, it's a bit different. We'll talk about that in class. Now the current in each resistor adds to the total current of the circuit, just like the water branching off. This will actually get us to, and I'll go over the derivation of this in class, equivalent resistance of a circuit. So if I've got a series circuit, a resistor R1 has, let's say, 3 ohms, R2 has 1 ohm, and R3 has 4 ohms. Then that means, as far as the battery can tell, because it doesn't know what sort of circuit it's hooked up to, but it just feels a total resistance of 3 plus 1 plus 4. So 8. Okay, not too bad. A parallel circuit's a bit different. If I've got a parallel circuit hooked up, and I've got R1 in one branch of the parallel being 1 ohm, I've got R2 being 3 ohms, and I've got R3 being 4 ohms. Then it's a little bit different. Then I can find the equivalent that the battery feels, the resistance of the circuit, as 1 over my equivalent resistance of the circuit will equal 1 over R1 plus 1 over R2 plus 1 over R3. Nice. So once you solve that out, well, I'd end up with a common denominator of 12 among these, so I'd get 1 over my equivalent would be 12 over 12 plus 4 over 12 plus 3 over 12. And 12 plus 4 plus 3 is 19, so 1 over my equivalent resistance would be 19 over 12, which means to solve for my equivalent resistance, all I'd have to do is flip this fraction. So that'll be 12 over 19, and that would be that. And that actually simplifies down to, let's see, about 0.63 ohms. So a parallel circuit is actually a really good way to put together a bunch of resistors and get an overall resistance that's less, which is kind of weird to think about. Now, in a circuit, there's energy that's stored. If you remember that voltage is just the energy divided by the charge, so joules per coulomb. Well, that means the energy in a circuit is coulombs times volts. Delta U equals Q times V. Now, the only reason I'm mentioning that is because it's useful for deriving the equation for the power in a circuit, which is what we're going to use more often. So you learned in the fall semester that power was a change in energy over time. We did that powerful as a horse activity where someone ran in front of a motion sensor, we measured their velocities before and after they started running, found their change in kinetic energy over time, and that was their power in watts. So power is just change in energy over time, but in a circuit, we learn that the change in energy is the charge times the voltage, QV. So the power is QV over T. Well, I can rewrite that as Q over T times V. And look at that. Q over T is just current, charge divided by time in a circuit. So that means the main takeaway that you'll need to know is that power equals current times voltage. And that'll get you the power of the circuit in watts. Okay, so those are just the basics of it. When we get back to class, we will start doing some circuit analysis. A great time will be had by all, and look forward to seeing you then. Take care. Bye.